Welcome to the deep dive. Today, we're going to be exploring this paper called Immune Defense, a novel adversarial defense mechanism for preventing the generation of adversarial examples. This paper proposes a really intriguing kind of a new approach to DNN security. We've got a lot to unpack here.
Yeah, it's really fascinating. I think it's a departure from, the usual reactive defenses that we see. Instead of trying to sort of patch DNN vulnerabilities after the fact, immune defense aims to stop adversarial examples from ever being generated in the first place.
That's right, and you know how crucial that is. We've seen how gradient-based attacks, optimization-based attacks, and generation-based attacks, they can all exploit those vulnerabilities and lead to, misclassifications, which can have, potentially serious consequences.
Yeah, absolutely. And existing defenses, while they are helpful, they often kind of fall short. Things like adversarial training can be really computationally expensive, and even then, they still leave these gaps and input pre-processing techniques. They can degrade image quality, and then you have detection methods, which are always playing catch up.
It's like, trying to plug holes in a dam, right?
Yeah.
You're constantly reacting to the latest leak.
Precisely. Immune defense it flips the script. It focuses on immunizing the images themselves, and it does that by introducing these carefully crafted perturbations. They call them immune perturbations, or IPs. And these IPs, they essentially create like a protective shield around the image, and they disrupt the attacker's ability to actually generate those adversarial examples.
So instead of fortifying the DNN, we're fortifying the data itself. That's a pretty radical shift in thinking.
It is. And it raises some really interesting challenges too. The authors highlight, this delicate balance of crafting these IPs. They have to craft them in a way that disables the attack while also making sure that the image integrity is maintained. They want to make sure that the DNN can still classify the image correctly.
That makes sense. It's almost like a cryptographic puzzle, right?
Yeah.
You want to make the image unrecognizable to the attacker's algorithms, but still readable to the intended recipient, which in this case, is the DNN.
Exactly. Now, the paper goes on to really delve into two main approaches for achieving this: white box and black box defense. Let's start with the white box scenario where, we assume the defender has full knowledge of the attack.
Okay, so in this case, we know the attacker's playbook.
Yeah.
How do we craft those IPs to counter their specific moves?
Well, so the paper outlines two methods for this. The first one utilizes gradient sign descent, or GSD, to minimize the classification loss of both the immune example, which is the image with the IP, and its corresponding adversarial example. The idea here is to basically make them indistinguishable to the attacker.
So we're essentially forcing both the original image and the potential adversarial example into the same classification bucket, making it impossible for the attacker to distinguish them.
That's a great way to put it. Now, the second approach they outline uses atom optimization, and it's used to minimize a multi-objective loss function. And this allows for much finer control over, those IPs, potentially leading to better performance and visual quality.
Interesting. So both methods, they aim for the same outcome, making the image immune to that specific attack, but they use different optimization techniques to get there. Are there any trade-offs to consider here?
Yeah, there are some trade-offs. Based on the experimental results, they found that the optimization-based approach yields superior IEs, both in terms of the accuracy and the visual quality. However, it might not be as effective against attacks that the defender is unaware of, which kind of brings us to black box defense.
Right. The real world is rarely a perfect white box. Attackers are constantly evolving their techniques. How do we create IEs that can stand up to unknown threats?
This is where the concept of transferability really becomes crucial. It's essentially, how well those IEs crafted for one specific attack generalize to other attacks, attacks that they haven't seen before.
Right.
So the authors propose a method called masked gradient sign descent, or MGSD, to try and enhance this transferability.
Okay, MGSD. All right, I'm all ears. Walk me through it.
So imagine you're trying to create an IP that's robust to a variety of attacks. MGSD strategically masks certain gradients during the optimization process. This masking acts like a filter,
Right.
It reduces approximation error, it stabilizes the updates, and ultimately it creates IEs that are more adaptable to unseen attacks.
So it's like we're we're training those IPs on a more diverse set of examples, even though we don't actually know the specifics of those examples.
That's a good analogy. And to help kind of visualize this, the paper provides a really helpful illustration in Figure 2.
I remember seeing that. It really helps clarify, how MGSD works. Now, before we move on to those experimental results, I wanted to touch on the metric they use to measure the effectiveness of these immune examples. They introduced this thing called the immune rate, or IR, and they make a pretty strong case for why traditional metrics like attack success rate or ASR and its variance, they kind of fall short in this context.
Absolutely. ASR really focuses on how many adversarial examples successfully fool the DNN. But with immune defense, we're trying to prevent those adversarial examples from even being generated in the first place. And the immune rate, as defined in the paper and calculated, using the data in tables 1 and 2, it really captures this crucial distinction. It quantifies the percentage of images that are successfully immunized against these attacks.
So it's a measure of how effectively we've raised the attacker's bar, so to speak.
Precisely. And it's a much more relevant metric, for evaluating the success of immune defense. So are you ready to kind of dig into those experimental results and see how these, different approaches perform in practice?
Absolutely. Let's see what the numbers say about the efficacy of immune defense.
Yeah. Okay, so let's dive into the white box tests first. As we kind of suspected, the optimization-based approach, the one for crafting the IEs, it really shines in this controlled setting. It achieved the highest accuracy, and it produced IEs with much better visual quality compared to, the gradient-based method.
Yeah, that's not really surprising, is it? Given its ability to kind of fine-tune those IPs to that specific attack. But I'm more interested in, the black box performance. How well did the IEs, especially those generated using MGSD, how'd they hold up against unseen attacks?
Yeah, that's really where things get interesting. So they tested the IEs against Advajan and Advajan plus C, and those are two really powerful generation-based attacks. And even without knowing the specifics of those attacks, MGSD still significantly outperformed the baseline methods in terms of transferability.
So even in a more, realistic black box scenario, MGSD delivered on its promise of robust, generalized protection.
It did. And they didn't stop there. They actually took MGSD a step further, and they integrated polyac momentum, PM, and variance tuning, VT, which are techniques that are known for boosting the transferability of adversarial examples. And the results were really quite striking.
I'm guessing those enhancements kind of pushed MGSD's performance even higher.
Oh, absolutely. Yeah, their best performing method, which they called VT MGSD, it achieved near perfect accuracy and incredibly high IRs against this wide range of black box generation-based attacks. I mean, that's a major leap forward for DNN security.
That's remarkable. But even the most groundbreaking research has its limitations. Did the authors address any potential weaknesses or areas for further exploration?
Of course. They acknowledge that attackers could eventually develop countermeasures to kind of detect and disrupt those IPs. And they really emphasize the importance of future research, kind of focusing on enhancing the robustness of IEs against these potential countermeasures.
Yeah, it's an ongoing arms race, right, as with any security measure. But this research really lays a strong foundation for future innovations in this area.
Absolutely. They also conducted a thorough ablation study, where they examined the impact of various parameters on the performance of immune defense, and this provides some really valuable insights for researchers who are looking to build on their work.
I always appreciate a good ablation study.
Right.
What were some of the key takeaways there?
Well, one thing they found was that increasing the number of iterations during that optimization process, it generally improved performance, but it also increased the computational cost, which is a pretty familiar trade-off that we often see in machine learning. They also discovered that the size of that immune perturbation, it really needs to be carefully considered. If it's too small, it might not be effective, but if it's too large, it can actually degrade the image quality.
That makes sense. It's all about finding that sweet spot between effectiveness and imperceptibility. Any other interesting insights from that ablation study?
Yeah, one more. They found that larger step sizes during optimization, they tended to lead to better transferability.
Hmm.
And that suggests that, maybe a more aggressive optimization, could yield more robust IEs.
Interesting. It seems like there's a lot of potential for fine-tuning those parameters to achieve that optimal performance, in different situations.
Hmm.
Now, before we wrap up, I kind of want to zoom out a little bit and think about the bigger picture here. What are the real-world implications of immune defense? This research has the potential to be, truly revolutionary, don't you think?
I completely agree. The potential applications are vast and they're incredibly exciting. Just imagine, security cameras, self-driving cars, medical imaging systems, all of them equipped with this proactive defense mechanism. Think about how that could transform fields like, facial recognition, object detection, even content moderation. It really could. We're not just talking about incrementally improving DNN security. We're talking about a fundamental shift in how we approach it. Imagine a world where these critical systems are inherently more reliable and more secure simply by design.
It's a powerful vision, and this research, it really takes a bold step in that direction.
Mm.
I think this paper marks a significant milestone towards a future where DNNs are not only incredibly powerful, but also, secure and trustworthy.
I think so too.
All right, let's do a quick recap of the key takeaways for our listeners today.
Yeah.
We started by discussing the limitations of those existing adversarial defenses, highlighting how they often, fall into that reactive trap of constantly trying to catch up with these evolving attack strategies. And then we introduced this idea of immune defenses, this innovative approach that flips the script, right? It focuses on protecting the data itself rather than just the DNN.
Exactly. And we really kind of dug into those two primary methods for crafting immune examples in that ideal white box setting. We talked about the gradient-based approach when we talked about that more precise optimization-based approach. And then we kind of tackled, the complexities of black box defense. We emphasized how important transferability is, and we explored the remarkable performance of MGSD, especially when, it's enhanced with PM and VT.
Right, and let's not forget about that key metric, the immune rate, which gives us a much more accurate way to measure the effectiveness of immune defense. And of course, that ablation study was incredibly insightful. It revealed how all those different parameters can be fine-tuned to really boost performance. That the potential applications of immune defense they're really far-reaching and honestly quite inspiring.
I think it's a testament to the incredible ingenuity and the dedication of researchers in this field. This paper opens up this whole new avenue for DNN security research, and it's really an exciting time to be a part of it.
It certainly is, and for our listeners out there, remember the pursuit of truly robust and secure AI is an ongoing journey. This paper, it marks a significant leap forward, but there's still so much more to uncover and understand.
That's right. Stay curious, keep learning, and who knows, maybe you'll be the one to develop that next groundbreaking, defense mechanism.
That's a great point. Well, thank you for joining us for this deep dive into immune defense. We hope you found it as thought-provoking and fascinating as we did.
Until next time, keep exploring the ever-evolving world of AI.
That's the deep dive for today.